Okay, hey, so sorry that I forgot to make this video earlier. Please forgive me. I was looking at kittens and lost track of time. Okay, so Webwork 8, problem 5. We'll look at two different functions. So one of them is 3e to the negative 6x squared. Sorry, I'm like looking and writing at the same time, and it's so tricky. And then the other one is f of x equals natural log of 9x squared plus 1, for example. All right, I have something on my screen here. There we go. Okay, so this is number 5. Right, we need to find the points of inflection. So let's go ahead and take a derivative of f. And you know what? I'm going to go ahead and call this thing g, just that way I can do them both and be less ambiguous. Okay, so take the derivative. And here's the thing. We need to think of f as 3, that's the wrong thing, 3 exp of negative 6x squared. We don't need to think of that. But a very common mistake for students is to think the derivative of e to whatever is e to whatever. So sort of you take the derivative of this, and there's whatever you want in here, and it's just the same. And that's not true. The true statement is that the derivative of e to, and now how should I describe whatever? Well, it can just be some function of x, so I'll call it u. Okay, so e to the power of u of x. If I take that derivative, there's a chain rule. And so the derivative of the outside function, which is the exp function, is itself. The derivative of e to the is e to the but the chain rule says then you take the derivative of the inside. So then you need a u prime. Okay? So in this form, if we take the derivative of f, hopefully we can see we have 3, and then the derivative of the exp function is exp. It's analogous how, so the derivative of sine is cosine, the derivative of cosine is minus sine, and then the derivative of exp is exp. Okay, so I'm not specifying what's in here, right? It's just those functions, these are the derivatives. Anyway, okay, so it's exp and you leave the inside alone, times, and now chain rule says take the derivative of the inside, so that 2 comes down, you get negative 12x. All right, but the way we typically write it is if I combine the negative 12 and the 3, I have negative 36 with an x, and then e to the minus 6x squared. All right, that's what this whole business is. All right, so now we need to take another derivative, and we should use a product rule because I have a product here. So take the derivative of the first function, it's negative 36. Leave the second function alone. Plus, and now you leave the first function alone, negative 36x, times the derivative of the second. And we've already done the derivative of the second. It's right here. So there's a negative 12x e to the minus 6x squared. All right, great. So now we need to clean this up a little bit, be able to make sense of the second derivative of x is equal to 0. This is sort of where we're headed in order to find points of inflection. Okay. So how do we clean it up? Well, factor out as much as you can. In this case, that includes the exponential part, x squared. And so what's left over? Well, in this first term, you have 1 plus, and in the second term, we factored that out, not the x, sorry, factored that out and that. So we're left with, we have an x and a that. So let's go ahead and write negative 12x squared. All right, so this is the form we're going to want to deal with the second derivative in. So let's go ahead and set it equal to 0. All right. So 0 is equal to negative 36 times e to the minus 6x squared times 1 minus 12x squared. All right. So if you multiply two numbers or three numbers, the only way that you can ever get 0 is if at least one of the numbers is 0. Well, so look, if we divide out the minus 36, that's never 0. We don't really lose anything. So, all right, now we need to look at this. All right, again, I'm multiplying two numbers. Number 1 is in this costume. Number 2 is in this costume. All right, and the only way to get 0 is if at least one of them is 0. But, you know, e to the, and then whatever you want, it's never going to equal 0. It's never going to happen. And essentially, if you think of e to the x, this is going to be 1 times, and then you need some copies of e here, right? You need x many copies of e, where we include fractional copies of the radicals. And you're not going to get 0 there. You're never multiplying a 0. Those aren't 0, right? It's not going to happen. So that's one way to think of it. And so in fact, this whole term, you can just divide it away as well. And so now solving the second derivative equals 0 reduces to just solving this polynomial. Whoop, that's not what I wanted. Sorry. This polynomial is equal to 0. Sweet, let's solve for x. So we get x is equal to, and I guess move over the 1, divide by 12, and then take a square root. But we need to remember to include the negative square root, so or negative 1 over 12. All right, so these are the x values for where the second derivative is 0. Now we need to check that the second derivative changes sign. So I'm going to do similar sign testing to what I've done before. I'm going to put down the negative 1 over root 12 and then the positive 1 over root 12. And check the sign of the second derivative. It's 0 here and it's 0 here. So what about in between? Well, let's plug in 0 and we get 1. 1 is a positive number. All right. And let's plug in something over here. Well, I mean, really, we have an x squared. And so if you plug in something over here, it just has to be more negative than negative 1 over root 12. Plug in 100, right? What happens? The negative wins. So we can see that it's going to be negative. And it turns out it's going to be negative over here too. Again, you could just plug in 100 for x, and you could see you have 1 minus something big. That's going to be negative. Okay, so do we change sign? Yeah, we go from a negative to a positive, back to a negative. So indeed, these two x spots are my points of inflection. All right, so same thing, new function. Get rid of all this. All right, let's take a derivative. So I have an outside function. Let's take the derivative of it. Let's leave the inside alone. 9x squared plus 1 times, and now let's take the derivative of the inside. So that 2 comes down, we get 18x, and the 1 is dead. So there we are. This is g prime of x. Right, so what I used was the derivative of natural log x is 1 over x. And if there's something more complicated in here, like some kind of function, it comes down, and then you multiply it by the derivative of the inside. Okay, so let's clean this up a little bit. Let's move that 18x over here. 18x. All right, now we need to take another derivative. Let's go ahead and use that quotient rule. So if I have a function over another function, then it's the derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. And some people like to say low d high minus high d low. That never helped me because I would switch the orders on accident and say like high d low minus low d high. Like what's going? So the way I finally was able to remember it is the function that's on bottom is feeling kind of negative when you take its derivative. So, all right, whatever. We're gonna take we're gonna use a quotient rule to take a derivative. So derivative of the top 18 times the bottom 9x squared plus 1 minus the derivative of the bottom 18x times the top 18x all over that bottom squared. All right, 9x squared plus 1. All right, we need to figure out when is this equal to 0. So we're going to set and solve. Well, good news, the bottom, never 0. I have something positive, and I'm adding a 1, and I'm squaring it. That thing's never 0. Let's go ahead and just multiply it away. So I multiply both sides by 9x squared plus 1 squared. And on the 0, it's still 0, but now on my left-hand side, I just have this numerator. Let's go ahead and clean it up a little bit. Do I want to? Actually, I'm not going to clean it up. I'm just going to combine some stuff. So I have 18 times 9 minus 18 times 18 for these two. And that's what's the coefficient on x squared. And, well, wait a second. 9, that's half of 18. So, in fact, what's left over, you could... All right, let me say this differently. Factor out the 18. This is gone. This is gone. You have a negative 9. So because I didn't make it all big numbers, I can kind of see really quickly that the coefficient on x squared is negative 9 times 18. And that was done by factoring out the 18 to combine everything. All right, and now we also have this 18 times 1. Anything else? Nope, that's it. So plus 18 times 1, let's go ahead and put that in front because it's positive. And all of this is by itself now because we cleared that denominator. All right, solve for x. Well, let's just divide the 18s away. All right, so now if I solve for x, I get x is equal to plus or minus the square root of 1/9, better known as plus or minus 1/3. Okay, that's pretty nice. Let's just add another piece of paper here. So now we need to check that G double prime changes sign at each of negative 1/3 and positive 1/3. So at these spots, f double prime is 0. Okay, what about over in this region? Well, let's see, let's plug in something less than negative 1/3. How about negative 1,000? So if you plug that in for x, you'd square it, you get something big, and you take that away from 18, you get a big negative. Okay, so f double prime is negative. All right, my favorite number, let's plug in 0, you get 18, that's positive, so we're positive. By we, I mean f double prime. Plug in any value you want between plus or minus 1/3, and this computation here will be positive. Okay, plug in any value you want that's bigger than 1/3 into this function. Oh, I'm calling f, it's g double prime, and it's going to be negative. All right, plug in 100. 100 squared, that's 10,000. You're taking away this big number from 18, it's negative. Okay, so yeah, we change sign, right? So we have 2 points of inflection. One is when x is, well, one is when x is negative 1/3, and one is when x is positive 1/3. Okay, let me quickly just kind of skip through the web work to see any others. I guess another point of inflection exercise is the very next one. It's number 6. Again, this is Webwork 8. And you'll just have some kind of polynomial. For me, it was 4x to the 4th plus 23x cubed minus 9x squared plus 1. And this is f. And so now to find the points of inflection, let's take two derivatives. So f prime is equal to, the 1 is dead, the 2 comes down, I have minus 18x. The 3 comes down, that makes it x squared. 3 times 23 is 60 plus 9, 69. Plus 4 comes down, that's 16x cubed. Okay, let's take another derivative. X goes away, we get minus 18. The 2 comes down, that makes it an x, and then 60 is 120, and then another 18 is 138. And 3 comes down, x squared. Sorry, I'm thinking of, man, that's not so nice, but okay, fine, whatever. So that's 30 plus 18 is 48. And now we need to figure out when this is 0. We'd set this equal to 0. We're going to get two numbers, all right? Whatever the first root is and whatever the second root is. All right, there's going to be two different values that make this equal to 0. And likely, all right, here's the thing. We're looking at a parabola that opens up. So in fact, if we just graph f double prime, it's going to be this. The spots where it's 0, those are our roots. And in between the roots, it's negative, and over here it's positive, over here it's positive. So look, whenever you have a quadratic f double prime, you know you have 2 points of inflection. You have two roots, and boom, you're done. Okay, I'm lying a little bit with the algebra because it's possible you only have one repeated root. For example, x squared, that's only one root. It's when x is 0. It's called a repeated root. And then you could have no root, so like something like this. If this was f double prime, you'd have no roots, you'd have no points of inflection. But that doesn't apply here. Who cares? All right, what else do we got? 7, you all should be able to do. That's some curve matching and just some